Hi there, welcome to this lecture series on matrix algebra. This is lecture 3, part 2. The topic is matrices. So in part 1, we introduced the concept of matrices and some basic operations. And in this part, we will talk about properties of these operations and related topics. Okay, let's get started. Now first, let's go through some properties on matrix operations. So here I denote capital A, B, and C are just 3 matrices with the correct size, of course, to allow the operations I'm carrying out down there. And then little c is a number. Okay, so the first property is distributive properties. So if I do a plus b and multiply by a number c, and this is the same as multiply c on each a and b and then add it up afterwards. Okay. And the second property here is in addition. So the order in addition doesn't matter. If a and b are the same size, you can add them up, then a plus b equals b plus a. So I just want to mention these and these properties can all be proved directly by definition. Look at the definition of this operation and then you see the left-hand side equals the right-hand side. Okay, so the next one is if you have 3 matrices A, B, and C that of the same size that you can do addition, then the order doesn't matter. So if you do a plus b first and then add c on it, it's the same as to do b plus c first and add a after that. Okay, and then number 4 is multiplication. And here it has to be written specifically in this way. So assuming a, b, and c are of the proper size so that these multiplications can be carried out, then if I do a times b in that order, a is on the left, b is on the right, multiply by c on the right, and it's the same as, note that the order a, b, c must remain the same, a, b, c. But I can do b times c first and then multiply a on the left to it. This gives me the same thing. Okay? You can also prove it just by definition. It will be a bit lengthy to write out the element of this final product and then this final product, and you can compare that they are the same. And then the number 5 property will be if a and b are the same size, and you can do a plus b and multiply by a vector c, then this will be the same as if I do a times c first and then b times c also, and then I add up the sum afterwards. Okay, so all these properties proved by definition. So if we compare these properties of the corresponding properties for real numbers, we see that all these properties are the same as for real numbers. However, there are some exceptions. The first, when we do matrix operations, and they are valid only if the matrices A, B, and C have the appropriate sizes. Otherwise, it's not. The summation is the same. In the properties for summation, when you write a plus b, and you are implying that a and b are 2 matrices of the same size. And second, this is probably quite important, that is, matrix multiplication is not commutative. Okay. In general, a times b does not equal to b times a. And that is under the assumption that A and B are square matrices, that A times B and B times A are both defined but they will not give you the same final matrix. Okay, we'll follow up with an example soon. And lastly, it is possible to have that matrix A times B equal 0. So what is a 0 matrix? Well, that is the matrix where all the elements are 0. Okay, A times B can be 0, and even if the matrix A is not 0 and B is not 0. Okay, so non-zero matrix product can be a 0 matrix. We'll follow up with an example here also. Also, there is a triple product in the property when we write A times B times C. Okay, so here the product is defined only if all the sizes are matching that allow you to carry out this multiplication. So in particular, if A is a M times N matrix, then B must be a matrix starts with N times some number P, and then C must be a matrix with starts with the P times some number Q. Okay, so in that case, then AB, this multiplication will give you a matrix M times P. So this times that, and the final result will be M times P as its size. And then this can multiply with the C, because then this P matches this P. And also, if you multiply B times C together first, multiply this with that, and the result will be N times Q matrix. And then this can be multiplied on the left by a matrix which is M times N, so this N will match that N. So in the end, then this product here will result in a matrix of size M times Q, and then this product will be a matrix of size M times Q. So at least the size would match. Okay, one important comment here is matrix product is not commutative in general. So we can consider 2 by 2 matrix just to check there. Let's say I have A matrix, which is just A, B, C, D. And then I have a B matrix, which is 1, 2, and 3, 4. So they're 2 by 2, the simplest one. So let's compute A times B. If I carry out the computation A times B, so what will that be? That will be this one cross that one. So it's A plus 3B here. And this element is this one cross that. That's 2A plus 4B. And this element here will be this cross that, so will be C plus 3D, and then this element will be this cross that, will be 2C plus 4D. Okay, and then I can compute B times A also. These are square matrix, so this is defined, and if I carry out that computation, and then I will get this matrix. I'll skip the detail. By now we are familiar with the product. And then we compare A times B and B times A, and we look at each element. They carry different expressions. So in general, for just some coefficients A, B, C, D, these two matrices will not be the same. Let's take an example of two non-zero matrices, and the product of them becomes a zero matrix. So we have a matrix A, which is the following, 0, 0, 0, 1, and the matrix B is 0, 3, 0, 0. And I carry out the matrix product, 0, 0, 0, 0, give me 0, and 0, 0, 3, 0, give me 3 times 0 is 0, and then 0, 1, 0, 0 is 0 plus 0, 0, and then this one times that, 3 times 0 plus 1 times 0 is 0. So it's a zero matrix. Okay, so redundantly, I switch the order. I want to show you multiplication. If you switch the order, you don't get the same thing. So let's compute this matrix here times this matrix. And then if you carry out that, and this is what you will get. And it's no longer a zero matrix. Okay. So just another quick example to show A times B in general does not equal to B times A. Okay, so we have briefly mentioned it earlier, like a matrix could be considered a collection of row vectors or column vectors. Let's pick up that idea and take a look at matrix multiplications by rows. So let's set up. So A is an M by M matrix, and B is a M by P matrix. Okay. And then for the A matrix, I will consider it a collection of row vectors. So A1, A2 to AM would be the rows of A. So the first row of A is called A1, and the second row here, so on and so forth, and the last row. And the B matrix is just the B matrix. We write out all the elements. So here A multiplied by B is valid because N equals N. So let's say A times B is C. And then we want to see that what can we say about the C matrix at the end, and in particular the rows of C. So we make this observation that A times B, the product here, so if A is M times N and B is N times P, and then A times B is a matrix M times P. And if we take out the column and the first row of A, call this A1, which is a row vector, and then its size is 1 times N. And then if I take the B matrix again, it's M times P, so this N matches this N, I can do the product. So A1 times B now will be just of size 1 times P, so it becomes also a row vector. And if you write out the content of this row vector, and you see that it's exactly the first row of C. Okay, so the first row of C would be the product of the first row of A times the B matrix, and the second row of C will be the second row of A times B here, so on and so forth. And then the last row of C here will be the product of the last row in A times B. Okay, so let's take a quick example for some small matrices. Let's say I have A matrix, which is 2 by 2, A, B, and C, D. And then I call the first row A1. A1 is a row vector, A and B. And then the second row is A2, which is a row vector, C, D. And then the B matrix is 2 by 3, just 1, 2, 3, 4, 5, 6. Okay, so let's compute the first row in A times B. What would that be? Well, that will be this vector here, row vector, times this matrix. And then you see that you just take this and take all these column vectors and you do this element-wise multiplication and add up, right? So that will be 1A plus 4B here, 2A plus 5B here, 3A plus 6B here. Okay, and then the second row, A2 times B, will be just this vector CD times the B, which is carried out in a very similar way. So CD cross that, so I'll be 1C 4D plus 2C plus 5D here, 3C plus 6D here. So you see, each of them is a row vector of size of length 3. Okay, then the product A times B would be just assembling those two row vectors, A1B and A2B, we collect those two row vectors and form this 2 by 3 matrix, and you can easily verify this matrix is exactly A times B. Okay, so the previous observation has some applications. For example, let's ask the question, if I have the A matrix and I multiply one row of A by a constant C, what happens to the product A times B? Let's look at it. Okay, so I have A times B, which we say we could compute this by taking row vectors out of A and then form these row vectors A1 times B, A2 times B, and then assemble them into a matrix. And then if in the A matrix I multiply one row by a constant, say I pick up row 2 and I multiply by a little constant C, what happens to the final product? Well, we see that by this observation, all these column vectors will be the same. The only one that will be changed is this one, A2 times B is now CA2 times B, which is marked red, and the rest is the same. So in the product, what happens is just the corresponding row in the product will be multiplied by the same constant C. We remark that multiply a row by a constant is one of the elementary operations we talked about earlier. Okay, so the next question will be, what if I switch two rows of A? What happened to the product? Okay, so let's look into some details. Let's say this is A times B, as before in our setting. These are the row vectors. Now let's switch the first and the second row in A, and then I get a new matrix like this. So A2 is now the first row, A1 is the second. Then we see that A2 times B will be the first row here in the product, and A1 times B will be the second row, and the other rows will remain the same. So we see that what happens to the product would be the corresponding rows in the product just got switched. So we remark again, switching two rows is also an elementary operation we talked about earlier. So another operation that we talked about earlier is adding to a row a multiple of another row. Let's see what happens here. Okay, so the same setting, that's the original system, A times B. So what we want to do now is we take the second row in A and add to it the multiple of the first row A times a constant C. So what happens to the final product of A times B? Well, we know that all the other rows will not be changed because this will be A1B and there will be A3B, so on, A and B. The only row that will be changed will be the second row, that is the row that you add on top of that. And then what will be in this row will exactly be A2 plus C A1 times B, right? So we can distribute the B. I will get A2 times B plus C A1 times B. And then you see that what happens to the product here is exactly the same operation. That is, you will be adding on top of to the second row the multiple of the first row by a constant C. Okay, so this is the third elementary operation we talked about earlier. So we see that if we treat A as a collection of row vectors, we look at the row vector operation, these three elementary operations kind of is preserved in this matrix product form. Okay, so you might be wondering, what if I treat them as a collection of columns? Well, very good. So you can do that and it will result in similar conclusions. So let's take a look. Let's say again, A is a M by N matrix and B is a M by P matrix. And now let's take the B matrix and consider it a collection of column vectors. We call them B1, B2, and Bm. Okay? And then the product A times B, if it's A times B is a vector C, then the columns of the C vector are obtained by multiplying A to each column of B. Okay, so if you look at C and take out each column, then each column is exactly this A times the corresponding column, and then you put here. Okay, so you can check the matrix size. That is, A is M by N, B is M by P, so A times B will be M by P. So in the M by P, you can take out a column. The column would have length M. It will be M by 1, right? So, and then if you take A and multiply by the first column of the B, then you are having size M by N for A and N by 1 for B1. And then this product will give you a column vector of M by 1. And then you can write out the A times B and compare to this expression, and then you see it's exactly the same. Okay, a quick example. Let's say this is my A matrix and that's my B matrix. And then I will consider B as 3 columns, B1, B2, B3. That's the B1, and that's B2, and that's B3. Then I can carry out the computation A times B1, which is this matrix times this vector, which one can work out, will give you this number. And then A times B2, that's A, that's B2, and then you will get that vector. And A times B3 is this by that, and you will get this one. And then A times B will be a matrix whose columns are exactly those 3 that we just computed. AB1, AB2, AB3. You collect those 3 columns and you form this matrix. Here you fill in the numbers and that's what you will get. And you can easily verify this by computing a direct multiplication A times B, and this is what you will get. Now, we are now ready to introduce the concept of product of a row and a column vector, which we have observed that occurs repeatedly in the matrix product. Okay, so let's consider a row vector. We call it U. And a column vector, we call it a V. And they shall have the same length, which means length will be N, will be same. Then we can think of the U as a matrix of size 1 times N, and V is a matrix of size N times 1. Okay? Then I can define the product, U times V. It's valid because the N here is the same as the N there. Okay. So U times N would be, so you know you will be taking this times that, and you will multiply the corresponding elements, make all these products, and add them all up. And in the end, you will have a 1 by 1 matrix, which is just a single number. And there is another way of multiplying, that is, we switch the order, u and v, and we compute v times u. So v is m by 1, and u is 1 by n, and this multiplication will result in a matrix that's n by n. Okay, and this is what we will get. So it will be v1 times u1 will be here, v1 times u2 will be here, so on and so forth, and v1 times un will be here. Okay, and then you can go to the second row, v2 times each of them will be put here. Okay, and then all the way through to the last one. Okay, so this product v times u in the end will give you a complete matrix m by n. That's all for today's lecture, and next time we will look into more special matrices, and I hope you enjoyed this one, and I'll see you next time.